Hi, my name is Robert Thomas, and I'm an assistant professor of civil engineering at Clarkson University in northern New York State. My mission is to engineer concrete solutions for the next generation of civil infrastructure, and I'm here today virtually to talk to you a little bit about lunar concrete. My title, Space Concrete, the Final Frontier, is a bit of a joke. This is a quote from an old American TV series from the 1960s called Star Trek. It called out to me as I was thinking about this presentation, and what struck me was that 60 years later, space is still the final frontier. Our quest to learn more about the universe around us is one of the most quintessential engineering challenges of the modern day, and nowhere is that truer than in the civil engineering and construction sectors. For millennia, we have worked to optimize the design and construction of civil infrastructure, the systems and structures that keep society comfortable. But for millennia, we have been tethered to this planet that we call home. And all of that is about to change. Before we talk about that, let's take a short trip through the history of concrete. We hear a lot today about unlocking the secrets to Roman concrete. A lot of folks say that the Romans invented concrete, but that's not quite true. In fact, we have evidence as far back as 8,000 years ago of the Nabataeans building masonry cisterns with hydraulic lime mortars. And there's evidence of Egyptian societies making masonry mortars 5,000 years ago. The Romans built the Pantheon roughly 2,000 years ago. And it was almost exactly 200 years ago that an English bricklayer named Joseph Aspdin patented Portland cement, which is still the basis of nearly all the concrete we make today. Reinforced concrete didn't emerge until 1867 when a French gardener named Joseph Monnier used steel rods to keep his concrete garden beds from cracking. 20 years ago, and less than 150 years after the invention of reinforced concrete, construction began on the Burj Khalifa, which still stands as not only the tallest concrete structure, but the tallest man-made structure of any kind. And just a few years ago, cements were hydrated aboard the International Space Station for the first time ever. Let's talk about another critical date, December 7th, 1972. That was the last time a human being set foot on our nearest celestial neighbor, the Moon. Apollo 17 was the 11th and final mission of NASA's Apollo program, which visited Earth's moon 6 times between 1969 and 1972. Each mission provided invaluable data about the geography of the moon, the composition of its soil, the conditions of its atmosphere, and more. But by 1970, the cost of the Apollo program had become astronomical, the public had lost interest, and NASA scrapped its plans for further trips to the moon. Artemis, the twin sister of Apollo, is a fitting name for NASA's mission to bring humankind back to Earth's moon. Initiated in 2020, Artemis will bring the first woman and the first person of color to the moon. It will establish the first long-term human presence on the lunar surface, and it'll use the moon as a stepping stone to reach our next nearest celestial neighbor, Mars. As part of the Artemis mission, NASA's Moon to Mars Planetary Autonomous Construction Technology, or MPACT program, is developing technologies to support construction of key infrastructure on the moon. Repeated missions to the moon will require landing pads to prevent dust plumes, which can take hours to settle in the moon's low atmosphere. Extended human presence on the moon will require pressurized habitats and life support systems to protect occupants from the harsh conditions on the lunar surface. Broad exploration of the lunar surface will require roads, shelters, berms, and other civil infrastructure, and NASA has ambitiously targeted the late 2020s for the first demonstration-scale lunar projects and the early 2030s for construction of the first landing pads. The Microgravity Investigation of Cement Solidification, or MIX project, was a collaboration between NASA and Penn State that was really the first step in the development of lunar concrete technology. Its purpose was to understand how the reduced gravity of the Moon and Mars would influence how cements solidify. Would the pore structure be different? Would different hydration products form? Would they have different structural and mineralogical properties? Dr. Radwinska and her team at Penn State sent cement samples to the International Space Station where they were hydrated at microgravity, which is as close to 0 G as we can get, as well as at equivalent gravities to the Moon and Mars. They also prepared companion samples in the terrestrial laboratory at 1 G so we could compare the properties of space-hydrated and Earth-hydrated cements. They were kind enough to share some of those samples with us so we could study their microstructures and properties. And here you see 3 Portland cement samples with lunar simulant aggregates that were hydrated at microgravity, lunar gravity, and Earth gravity. One of the most obvious changes we see is the appearance of coarse air voids in the space-hydrated samples. It turns out that gravity is extremely helpful in consolidating the fresh concrete. We need phenomena like buoyancy to help air bubbles settle out of the fresh concrete, and these effects are diminished at lower gravity. Of course, we know that air voids represent stress concentrators inside the microstructure, and we know that these macroscopic air voids greatly weaken the strength of the material. But they also make it more permeable, which presents another problem for structures that need to be pressurized. And this is yet another challenge that we'll need to work to address. We wanted to learn about the strength of the material, but it's very expensive to send samples to the space station, so the samples we send are far too small to perform any mechanical tests. So we do something called nanoindentation, which is when we take a microscopic probe and indent the surface along a grid pattern to see how hard and stiff the material is at that location. This helps us understand the strength of the particles within the microstructure, which we can then feed into a numerical model that might help predict the structural scale properties. You can see here that the aggregate particles are quite hard, while the hydrated cement paste that binds them together is quite a bit softer. Interestingly, we find that the micromechanical properties don't change very much at reduced gravity, which tells us that the dominating effect of microgravity is actually on the consolidation of the fresh concrete and the resulting impacts on the air void structure. This is important because once we understand the mechanism at play, we can theoretically design solutions to overcome that effect. As I said though, the mixed study focused on Portland cement. And while it helped form a basic understanding of how cementitious materials might behave on the Moon or Mars, Portland cement is really not a viable option for lunar construction, and the primary reason is cost. Let's do a quick thought exercise. It costs about 2 million euros to transport 1 kilogram of material from the Earth to the Moon. And normal weight concrete weighs about 2,400 kilos per cubic meter. So let's say we want to construct a landing pad. Maybe it's 20 by 20 meters and 300 millimeters thick. That seems like a reasonable landing pad to land a lunar lander. This equates to about 120 cubic meters of concrete and a projected cost of 240 million euros just for transportation of the raw materials. Maybe we want to construct a 20-meter dome, some type of human habitat. Maybe it has 100 millimeter thick walls and sits on a 200 millimeter thick circular foundation. This is a pretty small habitat actually and could potentially house maybe a small handful of people. That equates to 200 cubic meters of concrete for a projected cost of 400 million euros just for transportation of raw materials. This is clearly not sustainable, so we need to find a better solution. That better solution is in-situ resource utilization, or ISRU. According to NASA, ISRU harnesses planetary resources at mission destinations to enhance the capabilities of human exploration. In other words, ISRU is using what's already there. Obviously, if we're to achieve a sustained human presence on the Moon, we need to learn to harness the resources it offers. In terms of construction materials, the Moon has rich resources in the form of lunar regolith. That's just a scientific term for the lunar soil. And on the right, you see an image of Buzz Aldrin's footprint in the lunar regolith from the 1969 landing. There's also some water on the moon, but it's relatively scarce, somewhat difficult to extract, and it'll need to be conserved. Fortunately, over the last several hundred years, concrete researchers have developed a pretty robust toolbox of technologies that can be used to make concrete. One of those technologies is geopolymers, or alkali activated concrete. Geopolymers are cement-like binders that are made by combining an aluminosilicate material with an alkaline activator. On Earth, we make geopolymers with fly ash or slag cement, but this technology works with just about any aluminosilicate material, of which the lunar regolith happens to be one. Interestingly, the lunar surface also contains some extractable alkalis, so the activators could potentially be produced using the principles of ISRU. And finally, geopolymers do require water for mixing, for workability and consolidation, but the geopolymerization reaction is actually water neutral, so that water could potentially be recaptured. So lunar regolith-based geopolymers seem like a pretty promising solution. But only a few hundred kilograms of actual lunar regolith have been collected from the 6 Apollo landings, and unfortunately, NASA is not about to give that away to a bunch of concrete researchers. Fortunately, however, various parties have produced what we call lunar simulants. These are carefully selected and graded mixtures of Earth minerals like volcanic glass and feldspar that can mimic the actual lunar regolith. Some of these are very basic simulants that model the geotechnical properties of the regolith, and some are more specialized simulants that mimic the chemistry or mineralogy quite closely. We've used a variety of simulants, including the one I show here, which is JSC-1A, which stands for Johnson Space Center 1A. And even though this is made from terrestrial materials, the supplies are still quite limited. And with JSC-1A, actually only 40 tons of the material were ever produced, and it's currently out of production. So these samples are still quite precious. Our colleagues at Penn State used JSC-1A and a variety of other simulants and a series of alkali activators to produce lunar simulant-based geopolymers. And again, they graciously shared some of the samples with us at Clarkson. One of the most interesting things we observed were the microstructures of the geopolymer samples, and here you can see an example of that. You can see a few large air voids in the image on the left, where the largest air voids are about 100 microns or 0.1 millimeters wide. But in the close-up image on the right, where the simulant particle in the middle is only about 25 microns wide, we can see that the simulant particles are joined together by a dense, continuous, and well-refined cementitious binder. Even without performing macro-scale testing, this tells us that the degree of reactivity is very high, which suggests that the material was going to be both strong and durable. Not all the geopolymers work well. Here's another sample with a different simulant and a different alkaline activator. And even in the very zoomed out view of the microstructure on the left, you can see that it's much coarser and more discontinuous than the previous one. In the close-up view on the right, you can see how the simulant particles are no longer well connected. The paste matrix between them is sparse and poorly refined, and this suggests to us that this combination of activator and simulant would perform poorly as a geopolymer. Practically, that means either the activator is a poor choice and perhaps a stronger concentration would lead to better polymerization, or the simulant might not be very reactive, indicating that lunar soils with this kind of composition are not suitable precursors for lunar concrete. Based on that, we could guess which regions of the moon could be mined for geopolymer precursors. Here's a third set of microstructures. This is yet another simulant and activator combination, and this microstructure is really somewhere in between the previous two. We've got a lot of coarse air voids in the image on the left, and in the image on the right, the paste matrix is fairly well developed, but still a bit coarser than the best performing mixtures. So again, maybe we need to increase the activator concentration to achieve better reactivity. But really what I want to focus on in this slide are all these air voids in the image on the left. We saw similar air voids in the mixed samples earlier, and we said the air voids would form stress concentrators and weaken the strength of the material. These air voids can happen due to reduced gravity like they did in the mixed samples, but they can also happen due to a variety of other effects. Reduced gravity is not the only challenge posed by the lunar environment. We also see dramatic temperature fluctuations and the lack of an atmosphere. On Earth, atmospheric pressure helps with the closing of air voids in the fresh concrete. The image on the left is lunar concrete formed at 1 atmosphere of pressure, and the microstructure is dense and well consolidated, and there are no macroscopic air voids to speak of. The image on the right is lunar concrete formed at reduced atmospheric pressure. The lower pressure means the air bubbles don't collapse. Instead, they remain in the microstructure as it hardens, leaving the very large air voids you see here. These air voids dramatically weaken the strength of the material, which is yet another challenge we need to overcome. By the way, NASA and partners have investigated using pressurized tents to provide some artificial atmosphere during construction, but this will come nowhere near the atmospheric pressure we experience on Earth. The weathering conditions on the moon are another critical challenge. Without an ozone layer, lunar structures experience much stronger solar radiation than Earth structures. They'll also experience significant temperature fluctuations and constant abrasion by lunar dust and microasteroids. We need to know that they'll hold up to these aggressive conditions, so NASA and our partners at Penn State sent some lunar concrete samples to the space station and put them outside in a special platform where they were exposed to the low Earth orbit for about 6 months. They flew the samples back to Earth and we cut them perpendicular to the exposed surface to look at their microstructures. Here you see 2 of those samples, where this black region at the top represents the exposed surface. The top sample experienced significant surface cracking, probably due to thermal cycling. The bottom sample experienced a lot less cracking. The difference here is that the bottom sample was fiber reinforced and the top sample was not. You can see some of the fibers right here. So we know from this that fiber reinforcement is probably going to be a critical part of lunar concrete in order to produce durable lunar structures. So clearly we have a lot of work going on and we're trying our very best to develop lunar concrete technology and solve the various problems that appear along the way. But at this point, I think it's very important to acknowledge that our part of this work is small. There are so many other material technologies being developed that are just as promising, if not more promising, than lunar geopolymers. There are calcium sulfoaluminate precursors on the moon that could be used to make ettringite-based cements. This image shows the needle-like ettringite crystals that are the basis of these high early strength binder systems. There's also microwave sintering of the lunar regolith, where the regolith itself is melted and fused together to form a solid matrix. This is probably the most mature technology, and a great deal of thought has been put into how it can be used to make landing pads on the lunar surface. Here's one iteration where a lunar rover could theoretically be used to autonomously grade, compact, and sinter the regolith, forming a landing pad. There are also a series of other technologies that are quite promising. But there's an even bigger picture beyond that. We've only talked about the construction materials part of developing lunar infrastructure. If we zoom out even further, we realize that the materials side of this challenge is still only a very small part of the mission. There are so many other barriers to extraterrestrial construction that need to be removed or overcome. We need to provide power and life support systems. We need to handle raw materials extraction and manufacturing processes. We need on-site testing and quality assurance. So while it's appropriate for us to have some pride in our work and the advancements we're making, it's equally important to have some humility and recognize that we're part of a tremendous multidisciplinary team working together to solve an enormous challenge. With that, I would like to thank my students, collaborators, and sponsors, in particular Soleiman Dawood and Peter Collins, who generated most of the data and samples that I discussed today. Dr. Redlinska at Penn State, who is certainly the world's foremost expert on lunar concrete. And finally, our sponsors at NASA, who've provided the financial support for this work. Thank you all very much.